All right, so yeah, beyond this fancy title, what I want to talk about is emergence. And just a quick introduction, I am Andrea. I am a theoretical physicist. I did my studies in Italy, then I traveled the world for a bit, as is customary. And around 1.5 years ago, I started an assistant professor position in material science at the Zernike Institute of this university. I keep the introduction to the point. What is relevant here is that during my bachelor and master studies, I was trained in what is traditionally considered hardcore physics, investigating the fundamental laws that govern our universe. And as I was getting a bit lost there in the mathematics of it, I learned about this concept of emergence, which definitely shaped the way I approach science now and shaped my career so far. So, in fact, I gave it a lot of thought during the years. I wished I learned about it sooner, and now I make a point of spreading the word around. So I will tell you today what is emergence in science and physics, why is it so important, and why and how it shapes the way we should look at modern physics and science in the modern era. And I start with a game. So by raise of hand, let me know if you know the rules of chess. Just the rules, how the pieces move. Wow, almost everyone. Very good. So that's what I expect. Keep it up, keep it up. Now only keep it up if, beyond the rules, you have some knowledge of the strategies, you play occasionally with friends or online. A few less, maybe 40%. Now keep it up if you think you can beat Magnus Carlsen, world champion for many years, until last week. There was a change. So now 0 hands. You'll be surprised, sometimes I still get 1 or 2. I don't know if it's overconfidence or people don't hear me very well. But the rules are the same. They don't know better rules than we do. So what is the difference? They know more advanced strategy. They have more experience in advanced combinations or depth of analysis. And I raise this point because of a beautiful analogy that Feynman, one of the greatest physicists of last century, made, that learning physics is a bit like watching a game of chess between gods. We don't know the rules, but we can check their moves. And from these moves, we can look at the board and we can try to figure out what the rules are. As a chess player myself and a physicist, I always liked this analogy. But the more I think about it, I realize that it lacks something for me. Because it sort of implies that in the end, the goal is to learn the rules of the game. And once we have that, the rest come naturally. But my point today is that this is not the case. And this is just the starting point. I'll show it with a very simple example. If we take the motion of celestial bodies, we know the rule quite well. Thanks to Newton, we know that 2 celestial bodies, 2 stars, 2 planets, will feel an attraction that is proportional to the product of their masses and decays with the square of the distance between them. The rules are clear, and with that, we can calculate precisely how these bodies move with respect to one another, as long as we have only 2. If we add a third one, suddenly we are not able to solve this problem. This is well known as the 3-body problem. It's been open for centuries. We have no solution in the general case. In fact, Newton is now dead for a few centuries again. We learned a bit more about gravity. Thanks to Einstein and their theory of general relativity, we have an updated equation, which is a bit uglier, but still fairly compact. Trust me on that. It's not that terrible. And it tells us a bit more about gravity. In fact, it allows us to predict the existence of black holes, gravitational waves. It allows GPS trackers to work. And yet, we are not one step closer to solving the 3-body problem. So an update of the rules did not help us there. This chase of the fundamental rules in physics and other scientific fields, it's what is at the base of what we call the reductionist approach. The idea that given a complex system, I can break it down into pieces, understand the rules governing those pieces, and taking it up together to the complex system I started with. And over the centuries, this approach kind of created a hierarchical structure in the scientific fields, starting from sociology, actually. You think that, this complex behavior of gene and people at a very high level, you can think maybe you can break it down in the end how people work, so how the brain works or how a gene works. And this is what psychologists deal with. These are, as you were saying, Tina, detached, at least since a few years ago. These were not really connected. But then you think, well, a brain is just a collection of neurons and cells. So this is really what a biologist should study. Then a neuron is just communicating with the others through chemical reaction. So in the end, that's the expertise of a chemist, and chemical reactions themselves are just the motion of atoms and electrons around. And we go down to this fundamental and more pure field of physics, with mathematicians being there giving us the language we need to describe all of this. While this is a fairly popular and even funny description of the different scientific fields, I oppose this kind of view in science, and I'm not alone. In 1972, Philip Anderson, another Nobel Prize in physics, wrote a beautiful paper called More is Different, that I encourage you to read if you want to delve deeper into this topic, saying, and I quote, that the reductionist hypothesis does not by any means imply a constructionist one. That the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. In simpler words, because this is the key point I want to make, emergent phenomena are phenomena happening in systems that are complex, in which these properties cannot be explained by the rules of their parts. In even simpler words, I'm telling that in modern science it is important to understand and learn that 1 + 1 does not equal 2. And if you don't believe me, I will prove it now. Again, by raise of hands, who likes chocolate? Oh, hands down. Who likes French fries? Oh, hands down. Who does not like where this is going? Chocolate and French fries are commonly considered delicious foods. Yet most people, and this is a divisive statement, I talked to a few friends, most people would not consider the combination of them to be particularly good. So this is an example of delicious plus delicious not being twice as delicious. And this is at the core of what emergent phenomena are. To go back to the science a bit, I'm not saying that we should abandon this reductionist approach. It is very important to understand the rules of the fundamental parts of our systems, and it brought us very far. In physics in the last century, understanding how these large and small scales work was extremely powerful. We learned more about gravity. Again, we use it in GPS and other technologies. At the small scale, we learned about quantum mechanics and the interaction of atoms and even smaller subatomic particles. And we have, again, not so nice, but trust me, fairly compact ways of describing these rules. And again, this brought us extremely interesting technological advancement as well. But I'm just saying that if we limit ourselves to just this reductionist approach, we are kind of blinding ourselves to the beauty of emergent phenomena that we see around us every day. So I want to point out the limitations of this approach. The first one is chaos. Chaos is actually well defined in mathematics and physics in the fact that chaotic systems are systems where changing just a little bit the initial conditions lead down the line to catastrophic consequences or very different dynamics. The three-body problem is an example of it. That is why it's so hard to solve. Our climate and atmosphere are another. If you heard the saying that the flap of a butterfly's wing in Brazil can set off a tornado in Texas, that's what they mean. If a identical twin comes out of the uterus before the other, that's a small difference in an extremely chaotic system that can have unforeseen consequences. So this is very general and applies to all fields. And the counter-argument usually is that that's just because we don't know all the details. If we had knowledge of every butterfly, every planet in the universe, every atom, and we had infinite computational power, we would be able to predict how these work. We have the rules, and we just follow through. The problem is that, first of all, there are some regularities across chaotic systems that stem from the fact that these systems are chaotic. It would not be possible otherwise. One is this phenomenon of synchronization that I show with this harmonic oscillator or these metronomes. This is a very famous video where you see that these are oscillating at the same frequency, but they are somewhat delayed. If they were separated on a table, they would just keep this delay forever in a simple and somewhat boring system. But they are communicating through this wooden plank. That makes the system chaotic and allows them to feel each other and reach a synchronized state. So eventually, they start moving together. The beauty of this is that this is a simple example that we can actually calculate mathematically, but the same phenomenon of synchronization is not limited to metronomes. The same mathematics can be used to describe motion of birds, the chirping of crickets, and the firing of neurons in our brain. So it's extremely general in systems that have nothing to do one with the other in terms of the fundamental elements. And that's the other argument I always make, that these regularities in emergent phenomena come in the same way often in systems that have nothing to do with each other. So I'll give you some example. This is a textbook representation of what atoms look like or how they are assembled in crystalline structures. You see these simple cubic, body center cubic, and whatnot. You see them often. In fact, if you take tennis balls and you put them in a cube, you find exactly the same arrangement. The reason is that this does not depend on the specific properties of atoms or tennis balls, which arguably are not the same, but they come just from the fact that this is an efficient way of packing balls. This was easy to explain. Something a bit harder, you can also agree with me that neurons and galaxies are not the same thing. Yet, if you take a picture of how neurons connect to each other in our brain, and you look at the picture of how galaxies connect to each other in the universe, they are remarkably the same, down to the mathematical description of it. And if you take the spiral coming of the Fibonacci sequence of number, you can see this spiral mathematically described everywhere in nature, from the DNA to animals and plants to atmospheric events, and again to the structure of galaxies across the scales. So this is proof that these emergent phenomena follow some rules of communication between elements that do not depend on the properties of the elements themselves. And this is where reductionists break down. We know this very well in the field where I work, which is material science, because we deal with these emergent properties every day. And we are learning actually from nature. We are learning, for example, that the chameleon skin has tissues that can stretch and that allow them to reflect and absorb light in different ways, which changes the color. And because we understood this principle, we can now create in the lab man-made phononic crystals that behave in the same way. We can do the same for the adhesion of a gecko on a wall, which is given by the large surface of contact, which you can also replicate in a glove. And we know that the extreme mechanical strength of the spider silk comes from the fact that the molecules are arranged in fibers that are bundled together at larger and larger scales, and we replicate the same idea with different molecules in fibers like Kevlar. I emphasize the word nature here for a specific reason, which probably resonates with the audience. How many speak Dutch? How do you say physics in Dutch? You raised your hand, huh?
Fysiek. Nee,
Natuurkunde. So nature is in the word. In fact, the word for physics itself comes from the Greek word physis, which means nature in Greek. The two were one and the same, and because of this over-specialization, these got lost. But what I'm arguing here is that going beyond reductionism in doing science nowadays means going a bit beyond this division between the fields and understanding that the communication between them in chemistry, physics, biology, and beyond sociology, that's really what we need to incorporate for an holistic approach to science that allows us to understand and appreciate these emergent phenomena that we see every day. Thank you for listening. That was one.